Welcome back to 3.8 optimization. Last time we learned about the gradient vector and the directional derivative. Today I guess is kind of an application of a gradient vector, but not really. It's more of an application of the second and the first derivative test that you learned in the Calculus 1 course. First of all, what did we say? So if fx and fy are both 0, which means the gradient vector is the 0 vector. So if the gradient vector is the 0 vector, then what do we know about the tangent plane? Well, let's say, let's graph a function that has fx and fy at 0 at a point. In this case, it would be at 0, 0, 0, basically. So f of xy, we put in our input. What we get is the gradient of f for this function is, the gradient of f is equal to negative 2x, negative 2y, right? So negative 2x and negative 2y. How do we graph this? This is a elliptic paraboloid, so it should not be very hard to graph if I can graph it right. Like that, and like that, and like that, and then something like that. Right, there you go. That's what the elliptic paraboloid looks like. And it has a fx derivative at 0 right here, and an fy derivative at 0 right here. And you can see that these two vectors can actually form a plane that dictates the derivative, that dictates the tangent plane, that dictates the normal vector. So in fact, if you find any two derivatives, doesn't have to be a gradient vector derivative, just any two old derivatives, and you know for them to be 0, then all of your derivatives will be 0. But that's besides the point. We know that the tangent plane is flat, or flat in this case meaning parallel to the x, or no, that's not x, y plane. So it's a z equals something, right? The tangent plane will be z equals something. So that is what it means to be optimized. That's what it means to be maximized or minimized or something else. Now, if you're maximized, what happens is your vectors, or no, not your vectors, your curves, your planar curves sliced by the x-axis. So if you have an like an x-axis planar curve, what will you have? You will have x, z. The z-axis will be here, and then the x-axis will be right here. So you could see right here, this graph. I'm just gonna make this blue, I guess. This slice right here, and this slice right here. Let me do this real quick and change it to blue. So yeah, the slice is, for this, in this case, the slices are parabolas, downward facing ones, and it's going left, right? So it's, the slope is changing from positive to negative. And this is what it means for our second derivative test in the single variable calculus course, which is calculus 1, to say that if the slope is going from positive to negative, then there is a maximum. Or in this case, if the slope is going to positive or to negative, then the slope is decreasing. So if the slope is decreasing, then the second derivative, the concavity, is negative. The concavity is it's concave down, right? So if it's concave down, you have a relative maximum, because it's going up, 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 and then it's going to go down, 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 down. So that's a relative maximum. This same thing is happening in the y direction, right? So if I just use purple in this case, and then we have this trace right here, you could see that the tangent lines are also going from positive to negative. So both fx and fy have to exhibit this behavior in order for it to be a relative maximum, right? Both fx and fy have to exhibit this behavior. Similarly, both fx and fy have to exhibit a concave up behavior if it wants to be a relative minimum, if the function wants to be a relative minimum. What if they don't? This is your very good friend, except it's kind of rotated on another side. This is the hyperbolic paraboloid, right? I would give you a picture of it. If it's orientated as x squared plus y squared, it looks something like this, right? It looks something like that with the with that axis and that axis. But in this case, it's oriented like this. So we have our y slice, or our x slice is a downward facing paraboloid, so the slopes are decreasing. It's going from increasing to decreasing. And in this case, the y parabola is going upwards instead. As you can see, it's going upwards. So the slopes are not decreasing. The slopes are increasing. So the concavity is up. So it's concave up. So it has a relative minimum. So this is what we call a saddle point. Saddle point. And when does that occur? It occurs when the derivative in the x direct, or when in fx or fy, the derivative or one of them is or I should say fxx and fyy, because fxx means the second derivative with respect to the x direction. Fxx or fyy, one of them is positive and the other is negative. Now, if they are both positive or both negative, then we have relative extrema, which means we have relative minimum or relative maximum. If they are not, then we have a saddle point. This is what a saddle point is called. It's an upward facing parabola in one, or this is what it looks like, is an upward facing parabola in one direction and a downward facing parabola in the other direction. So I want to build a little bit of intuition about the thing that we're going to discuss next, because it's going to seem arbitrary. This next thing is going to seem really arbitrary. So obviously, when we calculate our x's and our y's, we can't just do a simple number line or a sign chart like we did in single variable calculus. We can't just do that to determine our relative minimums and relative maximums. Instead, or we can do that in single variable calculus, but we can't do it in multivariable calculus because x's or fx can depend on both x and y. Like the chart that I drew for our chain rule, fx and fy, they both can depend on x and y, each of which can depend on other variables as well. But they both depend on variables of x and y. So you'd have to have like a plane, not a number line, a number plane or a number surface. And for fy, you have to have a number plane as well. So that's gonna get really, really ugly really, really quickly. So that's why we don't want to use the second derivative test. And then you also have f sub xy and f sub yx, which is not very fun to deal with. So what we end up having to do is there's four types of second derivatives: fxx, f sub xx, which means the derivative or the concavity of x in the x direction; f sub xy, or f sub yy, which is the concavity of y in the y direction, or the concavity of y when you slice a plane x equals k. You have f sub xy, which is the rate at which f sub x changes as you move towards y. And same thing for f sub yx, but there's a theorem which I've already mentioned that makes it so that f sub xy and f sub yx are the same thing. So f sub xy and f sub yx are both equal to each other. F sub xx determines the concavity in the x-axis. F sub yy does not determine the concavity in the y. Now, what does f sub xy and f sub yx do? It doesn't really determine concavity. It determines the change of f sub x in the y direction. So if we go back here, let's do f sub yx actually in this case, f sub yx. So if as we change y, how does x change? Or how does the slope with respect to x change as we change y? Is what we're trying to find. So this is actually quite a hard image to visualize, but let's just visualize it like right here, something like that, right? Or let me use a different color, green. Right, so for this slice. So as we move up, it looks like f sub y is a lot flatter here, right? And then it kind of moves down a little bit more. And the slopes of y move down as we get to here, and then it kind of gets back, or it goes back into normal when we get to here, right? In this case, in this place right here, it stays the same the entire time. But yeah, so that's what f sub xy and f sub yx is measuring. It's measuring how much it's moving in the or how much it's like tilting, how much the slopes are tilting and tilting back. It's a little strange, right? So f sub xy in this direction, I think this is a bad function to use, because f sub xy for this function is 0, right? So this function is not a very good function. I would try to get a better function later, maybe to illustrate this point. But the point is, if there's a saddle point, f sub xy is going to, so f sub xy is going to exist if there's a saddle point, is basically what I'm trying to say. And it's going to be large. Why is it going to be a large number? Because if you change the x direction, oh gosh, if you change the x direction, the y direction is going to change, right? And it's going to change pretty heavily. Imagine if the picture was not like this and the picture actually had slopes like this. It's going to change quite dramatically when you get to the maximum, and it's going to go back to its normal state. It's a little bit strange, a little strange concept, but that will prepare us for this next fact called the second derivative test. And this is the ultimate second derivative test for two variables. If f is a function of x, y, and its second partial derivatives are continuous, then we let f sub xx be a, f sub xy and y, or f sub xy or f sub yx be b, and f sub yy be c. So if ac minus b squared, which is we call that d, which is really strange, we call that d of xy. So if ac minus b squared, if f sub xx multiplied by f sub yy minus f sub xy squared, or f sub xy times f sub yx, if that's greater than 0, we have a local maximum or minimum. Now if a or f sub xx is greater than 0, then we go back to concavity. So if it's greater than 0, that means it's concave up, that means it's minimum. If a is less than 0, concave down, maximum. So yeah, think concave up and down. If ac minus b squared is less than 0, then we have a saddle point. If AC minus B squared is equal to 0, then we have a degeneracy. There's not enough information to determine whether or not it's a minimum, a maximum, or a saddle point, right? Like the hyperbolic parabola. If we actually go back to y squared minus x squared, there's not enough information to determine whether or not it's a minimum, a maximum, or a saddle point. We'd have to use something else. However, for some other functions, like the functions that we have right here, it's easier to determine that. So f sub xx and f sub yy. So like, why does this function work? Well, as I've said before, the f sub xy serves as a like a change in the x-axis as y changes. So if y changes like from a kind of positive slope there to a negative slope, it's kind of like a twisting motion, and the twisting motion creates a saddle point very easily. Now, if you have a big f sub xx and a big f sub yy, and especially if they're the same sign, if f sub xx and f sub yy are the same sign, then there's a very high chance that it's either both concave up or both concave down, and that would make it very easily be a maximum or a minimum. If they are different signs, then that's guaranteed, 100% guaranteed to be a saddle point. If f sub xx and f sub yy are different signs. So these guys, you could see that they're different signs. So if we weren't going at 0, 0, then it would be guaranteed to be a saddle point, because they're different signs. If they're different signs, this is definitely negative, and if we have negative minus something that's definitely positive, then it will be a negative. That means we have a saddle point. However, just because f sub xx and f sub yy isn't negative, or if they're the same sign, does not mean that it can't be a saddle point. It still can be a saddle point. It's just not, I don't think it's that common that it's going to be a saddle point if f sub xx and f sub yy are the same sign. However, we're going to work out these problems and we're going to see whether or not I'm right. Let's find all the local mins and maximums of this function. So what's the gradient? The gradient is, or the gradient has to equal 0. So f sub x equals 0 and f sub y equals 0. Right? That's our first step. We have to have f sub x equals 0, f sub y equals 0. Because even notice in this problem, the tangent plane to this point is still flat. Now it's kind of below the graph on the y-axis and above the graph on the x-axis, but it's still a flat plane, and that's what makes this thing work. If it wasn't flat, it wouldn't work. So f sub x equals 0. So what is equal to 0 is y minus 1 over x squared is equal to 0. And then f sub y is equal to 0. X minus 1 over y squared is equal to 0. Right, now we can work out a system. So the system is going to be, well, if you move y to this side, you will have y equals 1 over x squared. So you can put 1 over x squared over here. X minus 1 over x squared is equal to 0. Okay, let me move this a little bit up so that we have more space. So 1 over x squared is 1 over x to the 4th, and 1 over x to the 4th is x to the 4th. So x minus x to the 4th equals 0. So x times 1 minus x cubed equals 0. So if we move this question down out of the way, x times, and if you, I don't know if you know the formula, it isn't very important, but 1 plus x times 1 minus x plus x squared, or no, that's wrong, I'm sorry. Let's just put a negative out so that I can get it to x cubed minus 1, and that is equal to negative x times x minus 1 x cubed plus, or no, x squared plus x plus 1. A little bit strange, a little bit of a strange factorization, but You guys will get used to it. This is not solvable because b squared minus 4ac is less than 0. However, these two are solvable, so x can be 0 or x can be 1. So x can be 0 or 1. However, we can't have 1 divided by 0 in this case. So x actually can't be 0. X can only be 1. So y minus 1 is 0, which means y can also only be 1. So x equals 1, y equals 1 is the only point. So let's check 1, 1. In fact, before we check 1, 1, let's do the second derivatives. So, this is really, really dirty and disgusting. I don't like this. Let's... Oh my gosh. Oh my gosh. No. Okay. Take this entire thing. Shrink it. Thank you. This is our question. So f sub xx is what? F sub xx is negative x to the negative 2. So positive 2 x to the negative 3. So positive 2 over x cubed. Excuse me. F sub yy is positive 2 over y cubed. And then f sub xy is what? F sub xy is f sub x with respect to y, 1. So our AC minus b squared is equal to 4 over x cubed y cubed minus 1. 4 over x cubed y cubed minus 1. Or you could just calculate them. So f sub xx at that point, 1, 1, is 2. F sub yy at that point, 1, 1, is 2. And f sub xy at that point, 1, 1, is always 1. So we're going to say D, just capital D. I'm just getting you used to the notation. 1, 1 is equal to 3. So that's greater than 0. That means that the f sub xx and the f sub yy won against the f sub xy, and we have a victory. We have a extrema. So since f sub xx is positive as well, this is a local minimum. So 1, 1, local minimum. So that was actually quite labor intensive, and you're going to see that this is quite a labor intensive process, especially in this next question. G of xy is equal to 2y, or no, y squared minus 2y cosine x. So what's g sub x? That has to be equal to 0. G sub x is 2y sine x. Positive. That's equal to 0. And g sub y is what? G sub y is 2y minus 2 cosine x. That also has to equal 0. So what does that mean? There's a very, I guess, sleek thing that you could do that would make this actually way easier. And I'm going to show you what that is. But I'm going to tell you how I first thought of this question. I first thought of this question as, well, y has to be equal to 0, right? And sine x has to be equal to 0 according to the first question, like the first part of this question. So if y is equal to 0, this is automatically 0. So yeah, so there's two cases. Y is equal to 0 and sine x is equal to 0. First of all, y is equal to 0. At y is equal to 0, we have negative 2 cosine x has to be equal to 0. Right, so if negative 2 cosine x has to be equal to 0, then cosine x has to be equal to 0. Cosine x equal to 0 when? Cosine x equal to 0 when, or I'm going to put a 0 to 2 pi range to this. So cosine x is equal to 0 when x is pi over 2, 3 pi over 2. So 0 and pi over 2, 0 and 3 pi over 2 works. Now sine x is equal to 0 when x is what? When x is 0 and x is what else? 0 and pi. Right? So when x is 0 and pi, y is what? Y is so cosine of 0 is 1. Cosine of 0 is 1. So 2y minus 2 equals 0. So y is 1. And this is one pair. So 0, 1. And then when cosine's pi, we have 2y plus 2 equals 0. So y is negative 1. So this is another pair. And they have to be like that. They have to be like this. So you can have 0, pi, you can have pi over 2, 0, 3 pi over 2, 0, 0, 1, or pi negative 1. Those are your choices. Now, another neat thing that you can do with this sort of thing is you could also do, well, 2y is equal to 2 cosine x. Y is equal to cosine x. You can switch the cosine x. You can have 2 cosine x sine x is equal to 0. And if you know your identities, that means sine of 2x is equal to 0. So if you know that sine of 2x is equal to 0, then you know that x is 0, pi over 2, pi, 3 pi over 2. So you can get all 4 answers just by doing that. Then you can plug it back in and find your answers accordingly. At 0, sine's already 0, so you just have to worry about this. At pi, sine's already 0, yeah, you just have to worry about this. Pi over 2, at pi over 2, well, sine's not 0, so y has to be 0. At 3 pi over 2, sine's not 0, so y has to be 0. Right? It's a pretty neat way to work it out. However, I'm just gonna make this smaller for now, and then I will perform the second derivatives. F sub xx is what? F sub xx is 2y cosine x. F sub xy is what? F sub xy is 2 sine x. Right, I'm just doing, this is f sub xx, so I'm just taking f sub xx and taking the derivatives. Very simple. F sub yy is what? F sub yy is this. The derivative of this is 2. It's just 2. That's very nice. So what does that mean? That means d of xy, or ac minus b squared, or ac minus b squared, is equal to 4y cosine x minus 4 sine squared x. Now let's do each of our points, and let's see the result. I don't know if you guys can actually see that. I hope you guys can see that. Okay, we can see that. That's very good. So our first point is 0, 1. So 0, 1. Pi negative 1. What else? Pi over 2, 0. And 3 pi over 2, 0. 0, 1. X is 0. So f sub x, or yeah, x is 0. So cosine 0 is 1. 2 times 1 times 1 is 2. Times f sub yy, which is 2. Minus this squared. So 4 sine squared x. So sine of 0 is 0. So it's 0. So that's 4. Which means that is a relative, or the location of a relative minimum. Pi negative 1. Pi negative 1. Well, cosine of pi is -1. Cosine of pi is -1. But that's countered by the -1. So 2 times -1 times -1 is 2. And then pi, and that's 2 as well. And sine pi is 0. So that's 4. That's also a relative minimum. Pi over 2, 0. At pi over 2, cosine is 0. So f sub xx times f sub yy has to be 0. So 0 times 2 minus sine of pi over 2 is what? Sine of pi over 2, sine of pi over 2 is 1. So 1 times, 1 squared times 4 is 4. So it's -4, and I'm really sorry about my brother. But this, and I'm going to say to you right now, this is going to be 0 times 2 minus 4 as well. Because sine of 3 pi over 2 is -1, but you square it, so you get 1. Right? That's why I say that b squared is never negative. So that's -4, and they're both saddle points. So they're both saddle. So those are your points. And I'll probably graph this to see if I'm right later on. I hope I am. I hope there isn't a random relative max somewhere. But yeah, that is how you find the local minimums and maximums.